All right, today we're looking at a paper called Towards Scalable Pre-Training of Visual Tokenizers for Generation. And it gets right to the point, tackling this really fundamental paradox in latent diffusion models.
It really does. I mean, we all know the visual tokenizer, the VAE, is absolutely critical. But the problem is pretty specific.
Which is?
That standard pre-training, the kind based on reconstruction, has this major scaling flaw. If you invest more compute to get better pixel fidelity, your final image quality can actually, well, it can get worse.
That's the whole tension, isn't it? And this paper introduces a framework, VTP, or Visual Tokenizer Pre-Training, and it claims to solve this exact scaling problem by just changing the objective entirely.
Exactly. They are the first to really push for this joint optimization of three different signals all at once. Yeah. You've got image-text contrastive learning, so CLIP.
Okay.
Then self-supervised learning, or SSL, and then your traditional reconstruction loss. It's a much more holistic approach.
So the big takeaway then is that semantic understanding is what's really driving good generation. It's not just about how well you can copy pixels.
That's it. You need a latent space that's semantically coherent for the diffusion transformer to, do its job well.
And this approach is what unlocks scalability.
Right. VTP shows consistent improvement as you scale up compute, parameters, and data. Conventional autoencoders just don't do that. They totally stagnate.
And the numbers seem to back this up. I'm seeing 78.2% zero-shot accuracy, 0.36 RFID on ImageNet. But what really stood out to me was the speed.
Oh yeah, the convergence is 4.1 times faster on generation tasks compared to other advanced methods. And crucially, when they scaled up the compute, they saw a 65.8% FID improvement in generation quality.
While the baseline just hit a wall.
Hit a complete wall. And that gain, purely from a better tokenizer, that's the real breakthrough here.
It really feels like it changes how you should think about allocating compute. So let's start by digging into this foundation flaw. In an LDM, the VAE is there for compression, right? Big image becomes a small latent map.
Correct. We've always pre-trained it with a simple reconstruction goal. L1 loss, perceptual loss, that kind of thing.
So why is that strategy suddenly failing us now?
Well, historically, it made sense. We measured its success with what's called reconstruction FID, or RFID. If your RFID is low, you assume the VAE is doing a great job copying the data, minimizing pixel errors.
But the paradox, and this is so important for anyone working with these models, is that a great RFID doesn't mean you'll get a great generation FID. The GFID.
Precisely. And the GFID is what actually measures the quality of the final image from the diffusion model.
So you could have a tokenizer that's incredible at lossless compression, but when you actually try to generate something new from that latent space, the results are just meh.
Or worse, yeah.
But hold on a second. If my VAE can reconstruct an image with, say, 99% fidelity, how is it possible the final generator is worse? Isn't better reconstruction just definitionally better input?
That's the intuition that gets us into trouble.
Yeah.
It becomes really clear when you think about what the loss function is actually prioritizing. When you force that tokenizer to chase perfect pixel level accuracy, every speck of dust, every little bit of noise, all the high frequency texture, you're basically forcing the latent space to become a very, very accurate but also a very messy photocopy.
So the model gets obsessed with perfectly recreating the noise and texture, but it loses the plot on what the image is actually of.
That's the perfect way to put it. The reconstruction objective biases at the latent space towards all those low-level details. And that pollution, it pushes the representation away from the clean, structured semantic space that the diffusion model really needs to work with concepts.
So if the latent space is just a vocabulary of noise, the diffusion model has nothing meaningful to work with.
Exactly. It has a terrible vocabulary for creating new, high-quality images.
I do remember some earlier attempts to fix this, things like VA, VAE, or RePayE, where they tried to regularize the latent space. They were trying to inject some semantics, right?
They were, and those were important first steps. They showed that injecting some external semantic info did help, but they often used distillation or focused on very specific features. The key is they never really explored the scaling properties across huge compute and data budgets.
Which is where VTP really shines.
Right. They didn't solve the fundamental scaling flaw.
Okay, so we get the problem. Let's look under the hood at their solution, VTP. How does it redesign the whole paradigm to bake in that semantic understanding from the start?
VTP is built on this idea that the latent space absolutely must encode core visual semantics efficiently. So architecturally, they start with a vision transformer. a VIT-based autoencoder.
That feels like a deliberate choice.
It is. VIT encoders are just better at capturing global features compared to the old CNN-based VAEs. But they kept a pretty standard autoencoder design, a bottleneck, tested a few different dimensions.
So moving to a VIT-based architecture makes sense. But the real magic seems to be in that joint optimization, training 3 objectives at once.
Absolutely. So let's break down those 3 loss components. First, you still have the, let's call it the necessary evil, the visual reconstruction loss.
You can't get rid of it completely.
You can't. It's still made of L1 and perceptual loss. But, and this is the key, they use a really small reconstruction weight, a lambda of just 0.1.
So they're turning that dial way down to stop the pixel obsession from taking over. It's like a guardrail.
Exactly. It forces the autoencoder to focus on what's essential, not just the noise. Then you get the 2 big representation learning parts. Second is self-supervised learning, or LAS, built on Dino v2 practices.
And that's targeting local spatial awareness, making sure all the little parts of an image make sense together.
You got it. It combines masked image modeling, so reconstructing missing patches, to learn context and self-distillation, which uses an EMA teacher model to enforce consistency. It really sharpens that local perception.
And then the third piece brings in the global cross-modal intelligence you need for text-to-image.
That's the contrastive learning component, the likely loss. It just follows the standard CLIP framework, maximizing the similarity between image and text features. This is what gives the latent space a global semantic understanding that's already compatible with language.
So VTP is forcing the tokenizer to juggle 3 things at once. Keep enough pixel detail, understand local spatial relationships, and align with high-level concepts from language. It's a truly holistic way to define a latent space.
It is. But that joint optimization, it creates a pretty massive engineering challenge, specifically with batch sizes.
How so?
Well, contrastive learning, the CLIP part, it needs enormous batches to work well. You need to find those hard negatives. They used a batch size of 16,000.
Whoa, 16,000. That's a huge amount of compute just for the tokenizer pre-training.
It is. Especially when the other 2 objectives, reconstruction and SSL, they work just fine with much smaller subsets like 4,000 or 2,000. The real engineering genius here is how they manage the memory and compute to draw these different size batches for each loss function, all at the same time.
That kind of implementation detail is what separates a neat idea from a solution that can actually scale.
Absolutely. Without that complex batching, integrating CLIP at this scale just wouldn't be feasible.
Okay, let's get to the proof in the pudding. The results. The first experiments are just designed to confirm the paradox, and it's a perfect case study of what not to do.
It is. They took a standard reconstruction-only tokenizer and just scaled it up. And the results are pretty stark. The reconstruction fidelity got way better. The RFID dropped from 2.0 down to a really impressive 0.5.
So perfect pixels.
Perfect pixels.
Yeah.
But the generation quality suffered.
Right.
The GFID, the measure of the final output quality, it actually rose from 55.04 to 58.56.
Yeah.
So more compute spent on reconstruction actively hurt the final generation.
Textbook definition of the problem. Okay, so now what happened when the VTP hybrid approaches were put to the test?
This is where they established their core finding. Understanding is the driver. They measured semantic understanding using ImageNet Top 1 linear probing. They tested hybrids, like CLIP, plus a standard autoencoder. When these hybrid models were scaled, they showed stable, simultaneous improvement across all the metrics.
So basically, if the model gets smarter, the generations get better, even with the exact same downstream diffusion model.
Exactly that. They saw this really strong positive correlation between that linear probing accuracy and the final generation quality. So adding semantic tasks directly fights the negative effect of the reconstruction goal.
And when they used the full VTP framework with all 3 losses.
That's where it hit the highest marks.
Yep.
Best understanding performance at 74.9% accuracy, and the best generative performance at GFID of 27.8, all under the same compute budget.
What I find interesting is that it shows the generality of this idea. It doesn't matter if it's cross-modal CLIP or self-supervised Dino-style learning. Both help.
That's the critical observation. It's the semantic depth that really matters.
Yeah.
But the real breakthrough is in their second finding, superior scalability. This is where VTP proves it's a real paradigm shift.
Let's talk about that scaling across the 3 axes: compute, parameters, and data. With compute, you already mentioned that huge relative gain.
Yeah, 65.8% relative gain in generation performance when they scaled the pre-training compute budget by 10x. The baseline AE just plateaued immediately.
What does that actually mean in practice? Why did the extra compute finally start to pay off?
It means the compute was finally being spent on meaningful, high-level learning tasks. For the baseline, extra compute just made a slightly better photocopier. For VTP, the extra compute let the model build a much deeper semantic understanding.
Which translates directly downstream.
Exactly. The diffusion model starts with a much smarter vocabulary, so you get faster convergence and higher quality images.
That has huge implications for anyone planning out their infrastructure. What about scaling parameters? Does making the tokenizer bigger only help if you use VTP?
Absolutely. They compared a large VTP encoder with a large baseline autoencoder. The conventional AEL just stagnated.
Yeah.
Its GFID hovered around 57 no matter how big they made it. The model was huge, but the objective was dumb.
Whereas VTP used that extra capacity.
Beautifully, it showed this clear, consistent scaling trend. As the model size went from small to large, VTP's GFID just kept getting better, dropping from 31.28 down to 26.12.
Wow.
And they even found that scaling the decoder helped too. It seems VTP provides such a high-quality latent signal that the entire architecture benefits from more capacity.
So capacity finally starts to matter because VTP gives all those extra parameters a meaningful goal to optimize for.
A goal beyond just pixels. And it's the same story with data scaling.
Let me guess, VTP scales, the baseline doesn't.
Dramatic pattern. They trained on datasets from 100K up to 100M samples. The standard AE barely improved. Its GFID just nudged a little.
All that extra data was basically wasted on it.
Completely. Meanwhile, VTP's GFID dropped substantially, from 47.59 all the way down to 27.45. It just proves that this new approach unlocks the potential of large-scale data and parameter investment for the tokenizer.
Which is huge. It means the focus shifts entirely to making that first stage, the tokenizer, as smart as possible. You don't have to overhaul the whole diffusion training process.
Precisely. And when you compare VTP to other state-of-the-art methods, it holds a clear advantage. Take distillation methods like VAVAE. They converge faster than a standard LDM, sure, but their performance ceiling is just lower than VTP's.
And VTP is even faster.
4.1 times faster convergence than VAVAE. That tells you its latent space is just intrinsically better.
And what about the other approach, using fixed representation encoders like RAE?
Right, those try to reconstruct from the frozen features of some external model. The paper shows these often lead to really bad artifacts like color shifts and weird textures. The fixed features just don't align perfectly with what the autoencoder needs.
VTP avoids that by training everything from scratch while still building in that understanding.
It avoids the reconstruction flaws while achieving that semantic richness.
Yeah. This really feels like it shifts the bottleneck in LDM development. The evidence is just overwhelming. Pre-training has to be redesigned from the ground up to integrate high-level understanding if we want to keep scaling.
The evidence is very strong.
Yeah.
We're moving past the era where a good compressor was enough. We now need an intelligent one.
So this provides some of the first real conclusive evidence that these representation learning objectives, CLIP and SSL, are the key drivers for tokenizer scalability, which opens up some really interesting research avenues for you, the listener, to explore.
Two big ones come to mind. First, if combining these objectives is better, what other perceptual tasks could you integrate? Think beyond CLIP and SSL. What about losses that enforce, say, structural integrity or causality, or even a hierarchical organization of objects?
Building an even more powerful multi-objective pre-training framework, a truly multimodal tokenizer.
Absolutely. And second, since data scaling is now so critical for the tokenizer itself, we have to look beyond just the quantity of data. How can the distribution of that pre-training data unlock specialized skills?
What do you mean?
For instance, what if you pre-trained a tokenizer mostly on data that's really rich with fine-grained text or complex architecture? You could potentially unlock dramatically better capabilities for downstream tasks like logo generation or photorealistic buildings. The tokenizer is no longer just a simple utility.
It's the new foundational model.
It's the new foundation.